Well, Richard might have already convinced you that the math education for meteorology and oceanography needs to be modernized. Well, in the following, we'll discuss how to do it. So I like the recruitment statement of your department. The students can begin research projects in their freshman year. Well, to do this, a freshman may need to learn Python or R to analyze and visualize data in .nc format. She can read and plot, let's say, SODA data or Argo data, or he can find a paid internship in summer. So as students advance in their studies, and then they can use calculus concepts to solve real-world problems. They can explain assumptions of a math model and then tell stories about their results. However, these methods are not included in the 6 traditional math courses listed by Richard earlier. So let's now use examples to illustrate our method to teach the basic concepts of linear algebra, statistics, and calculus. But this is an example, everybody knows about it. The example of is the ENSO pattern. And so the top figure is ENSO pattern. So this is an example of computing and interpreting EOFs. It was computed from the January surface temperature data of the NCEP real analysis. The top frame is the second EOF and shows the spatial pattern of ENSO. And the bottom frame is the second principal component. It shows the temporal pattern of ENSO. One pattern shows what ENSO looks like, and another shows when ENSO happens. Students can download this data from our book website, use our R or Python code, and reproduce the figure in class, right in that classroom we teach, or when doing homework. So what is the math behind the EOF computing? Well, it is a matrix decomposition known as SVD, singular value decomposition. Space-time data matrix A can be decomposed into 3 matrices, a spatial EOF matrix U, a diagonal matrix D, and a temporal PC matrix V. For any space-time data, we use rows to indicate the spatial location and columns to indicate time. In the case of NCEP data, just index the grid boxes, the 1, 2, 3, 4, as the rows of the matrix. And then the month by 1, 2, 3, 4, etc., as columns of the matrix. Then simply use the computer command SVDA to output EOFs, PCs, and eigenvalues. And then again, so an EOF shows what a phenomenon looks like, and the PC shows when it occurs, and the eigenvalue shows how strong is the phenomenon. So when I teach SVD, I often use my bronchitis as an example to help students to understand it. So EOF shows the symptom of my bronchitis. PC shows the date of occurrence, and eigenvalue shows the seriousness of my bronchitis. So this is an example about the concept of regression. The x-axis of the left figure shows the elevation of the weather stations in Colorado, and the vertical axis is the mean July temperature. The black line is the linear fit, and the red line shows confidence interval of the fit. And the blue lines shows the confidence interval of the July temperature is a random variable. The right figure shows the residuals of the linear regression. So this is useful for checking the assumptions for linear regression. And then, so what are the assumptions? Well, is the model linear? Are the residuals normally distributed? Do the residuals have constant variance? Are the regression errors independent? However, very few professors explain these assumptions to students. A serial correlation is often a problem for regression. So this mistake is frequent in the published papers. This is an example to explain the basic ideas of calculus to somebody who does not know anything about mathematics. So can our students explain the calculus ideas to their grandpa or a 10-year-old sister? This figure might help. So people climb a mountain from A to B, and the road has different slopes. A step rises more at a location of a larger slope, and the total height from A to B is equal to the sum of all the rises of the steps. The height is called the integral of the slope, and the slope is called the derivative of height. So the height and slope go hand in hand and form a paired relationship. And this relationship is the basic idea of calculus. So when we know the boundary conditions at A and B, we know the total height, h, and then we try to calculate the slopes between A and B. So when we know the slopes between A and B, we can try to calculate the total height from A to B. So this figure might remind you of our time, your time in the calculus classroom as a student. So later you found that you would never use these formulas. So many of the methods we learned from the traditional math courses are not used in our research or practice, although they may become, they may be beautiful. For example, we do not use convergence tests of infinite series. We do not make hand computing of the determinant of a 4x4 matrix. So with the previous examples, so we ask a question: how do we learn and teach effectively? Richard has already quoted Confucius for our pedagogy philosophy. I say it here again. I hear and I forget. I see and I remember. I do, I understand. So the keyword is do. Modern video games take the full advantage of the do psychology. It provides players with instant gratification and an exciting experience. Can we do the same in mathematics? Now, we do not pretend that we know all the answers. However, inspired by Confucius pedagogy and the psychology of video games, we suggest using computer programming and real data to excite our students to learn by doing. In this way, students see results right away. They also may increase their hope of finding a very good job. The climate math provides many resources for learning and teaching, such as computer codes and solutions menu. The solutions menu in both R and Python are freely available to instructors by the publisher. So we propose this way to modernize the math education for meteorology, because we can utilize the abilities of today's students who have grown up with computers and smartphones. Our way leaves tedious algebra and trigonometry to computers so that we can focus on storytelling, concepts, assumptions, and physics. Students can concentrate on learning the math that will be useful for their jobs and for their research. So we often say, math does not change, but math is changing. So last year, BAMS published an interview with Richard and me. The title is The Changing Math of Atmospheric Sciences. It may be difficult for traditional faculty to teach this modernized math, but it should be easy for a newly trained PhD in climate science. While each institution may have its own way to identify qualified instructors to teach the modernized math. Well, how about a joint appointment between math and meteorology? How about having a designated math professor for climate science students? So modern math can fully utilize students' strengths in computer and IT skills. And math can be taught as stories, and math can be illustrated by graphics and data. Calculus, linear algebra, statistics, data science, and computing should be integrated together as a single course that is useful for jobs and research. So we need to hear the voices from students and their employers. Students deserve better. So we have some advices to students. So you need to let your voices be heard by professors, department chairs, deans, and even university presidents. So I will end our presentation by asking a few questions and leaving plenty of time for discussion. Are we ready to modernize our math curricula for today's big data environment? Can students remember, understand, and use what we teach? Aided by computers, can we teach the core and modern materials quickly in the first year and leave the deep and difficult traditional topics as elective courses to be taken later? So in summary, can we modernize math education for meteorology and oceanography? So we would like to discuss these questions with you. So students have unalienable rights of life, liberty, and pursuit of happiness. Thank you very much for your attention.